Ready. Okay. What I want to do next, and it's the last thing I'm going to do, is to try now to use this simple dynamics to explain how you set the stratification of the overturning circulation in a global ocean. It's of course a very idealized problem, but for the moment we just looked at the spin down problem, or I don't know if it's a spin up or spin down, because it has a phase of a spin up and then it spins down, mostly to understand the boundary layer structure. Now we want to go back and try to understand a bit how that stratification, which if you remember Paula reminded us yesterday, this is now a section of the Pacific, high latitude, low latitudes, depth, and these are density surfaces. You remember that Paula reminded us, or at least, and the community realized just over the last 20 years or so, that most of that stratification seems to be set in the Southern Ocean, where these isopycna are set by a combination of winds that try to tilt isopycnal upward. There is a strong equator Ekman flow and eddies that try to balance it, so you set this isopycnal, and then the rest of the ocean in a sense has to match this tensile stratification and bring it all the way to the interior. So we want to see how that happens for the abyssal part of the stratification, not the adiabatic part that Paula was talking about, in view of what we just learned. So in order to make progress again, we want to keep the problem extremely simple to at least, you'll see that it's complicated enough as it is. If you try to do more than that, it just confuses a bit the dynamics, but clearly there is a lot of work that needs to be done and everybody can contribute. For the moment, what we decide to do is that we know the time scale for the setup of this stratification in the Southern Ocean is probably decadal. Well, when you're talking about the setup of the stratification for the rest of the ocean, it's clearly a diffusive process. You're talking about thousands of years. So you can think about setting the stratification being a fast time scale and the rest being the slow time scale. And we're interested in the slow time scale because we're interested in what happens in the basin. So what we're going to do to mimic what happens in the Southern Ocean, we're going to rewrite the equation of buoyancy by adding a restore into a prescribed stratification to the south. So we say that happens very fast and we're just prescribing it. The question we are asking now is not the full solution including the Southern Ocean. We're just asking, if I know the stratification here, how does that stratification get communicated to the interior? Right? That is a lot in the spirit of what Paula described, but now we want to worry about whether the turbulence and these boundary layers have an important impact on what that solution looks like. So first, let's see, now I run my simulation, I let it equilibrate. Now I have a source term in the Southern Ocean through this restoring term, which mostly generates this dense water, and we know that in the rest of the ocean, in the net, the water will tend to rise, the boundary layer upwelling dominates over the sinking, we'll see in a second. So there is sinking or transformation of water from light to dense because of that restoring term in the Southern Ocean, and then we see what happened elsewhere. So now this, I'm showing a section across my numerical simulation from north to south. So this is the south and this is the north. This dashed line shows me what I call the Southern Ocean. It's still my closed bathtub, but it's the Southern Ocean and it's the area where I strongly restore on a time scale which is 1/100th of the diffusive time scale on this simulation. So here the stratification is prescribed. The first thing that you see is that in the upper part of the water column, the stratification essentially gets communicated all the way to the interior apparently. That's a bit like what Paula was saying. The stratification from the Southern Ocean gets transferred to the Northern Hemisphere. However, you also see that there is a lower component where the isopycnals that tend to quite outcrop into the interior. So there is a place where stratification is not communicated as directly in the interior. And that's not just a simple artifact of this simple model, because if you go back to your observation, you definitely see this isopycnal cropping in the interior. There is a lower layer where the stratification is not affected all the way to the Northern Hemisphere. So let's try to understand what this circulation looks like. Again, if I show again you a section, was there a question or no? If I show you a section in the Northern Hemisphere, east-west, I see again this pattern of upwelling or downwelling. So the boundary layer structure is essentially the same that you've seen before. It's still there, it's still developed. And that's where most of the diabatic transformation is happening. So you still advect light water up along the boundary layers and then light water down along in the interior. But I want to show you that the second thing that you start seeing in this solution, which is quite reminiscent of what I was showing before, I can now plot as a function of buoyancy or density. And now this is the transformation of the amount of transport across a density surface. Like the plots I've shown you before, I used Barbie force, now I use lines. But this is what you would call the overturning, the net transformation across a density surface that is up to some, this is all non-dimensional terms, 0.01 non-dimensional Sverdrups. But you see that this number is the cancellation of a lot of transport along the upwelling boundary layers and a strong sinking in the interior. Right? So that cancellation is also in this solution. I'm just trying to give you a bit of a feel that, yes, we still have the boundary layer solution, and that boundary layer solution gives us this big cancellation between upwelling and downwelling. But now we can describe a bit more what that solution really looks like when we finally have the full forcing in the Southern Ocean that can communicate and generate a large-scale circulation that transfer the information from where you set the stratification all the way into the basins. So again, this is across this section. And now I can start describing a bit what is happening here. This is the meridional velocity into the page. Now what you see is that there is a bunch of red here. There is a velocity going northward in the abyss. The thickness here is much larger than the thickness of that boundary layer. Indeed, that thickness is the Stoneman boundary layer thickness. For people that know, it's the thickness of the boundary layer in a rotating system, which is given by the ratio of beta and the frictional term that I use. So this is a boundary current at depth in the ocean that is bringing water to the north. This is what actually is advecting the stratification from the south to the north. It's advecting water mass property with their properties to the north. So this water arrives from the south and is transporting stratification towards the north. We can also look at the zonal velocity at the same time, so the velocity in this direction. You see that there is a very strong zonal flow from the left to the right. So what there is a boundary current that transfer property up here, and then a zonal flow that goes from the left to the right. And so I transport waters also on that boundary layer. Now all these waters that have been moved to the north and along the boundary layers on both sides can upwell along the boundaries. Right? They are transported to the north, they are transported zonally. There is only really a zonal flow. You don't see any meridional flow in the middle of the domain because we cannot cross PV contours in this system. I told you friction is very small in the interior. And that's indeed one of always the puzzle of the abyssal circulation. If I don't have any forcing in the interior, we said that there is not much of a vortex stretching, I shouldn't have any meridional flow. And indeed, unlike in Stommel's solution, now there is no meridional flow. It's only a zonal flow that develops here. So you have water that comes along a deep western boundary current from the south, and it keeps zonally transferring some property along the eastern boundary. So you have the water gets diabatically transformed only along the boundaries. There is no upwelling in the interior. It's all along the boundary. The water goes way up along the boundary, then it starts descending in the descending branch over the boundary layer. And now if you look at this picture, again, what you see is that there is a western boundary current that develops here. It's pretty thick again. That brings water south. So there is a second boundary layer that returns the water to the south after it has been turned into lighter water. And indeed, since the eastern boundary needs to communicate to the western boundary, there is also a zonal flow in the opposite direction above it. So there is water that enters from at the bottom from here, gets transferred there, goes up, transfers zonally back here, and then it returns south. And these two boundary currents are a deep boundary current and a shallower boundary current on top of each other that allow the stratification. They're all on the western boundary because that's the only boundary where you can support this zonal flow, this meridional flow. And they can exist because they are essentially abutting against topography where there is friction, so they can cross PV contours. They cannot do it in the interior. So we still have boundary currents a la Stommel, but we don't have any meridional flow anymore. The exchange flow is water coming out in a boundary current at some depth and returning at a different depth. You can actually show it even more compellingly if you take a section right across the equator, where we're not going to go through the detail, but the boundary layer thickness becomes very thin at the equator, so you're only left with the western boundary current a la Stommel there. And now you really see that there is only a northward western boundary current here and a southward western boundary current above it. That's the big meridional exchange of waters. That's what sets the stratification. I advect along the western boundary and I return along the western boundary, but all the transformation happens instead along the boundary when I have this upwelling and downwelling confined to the boundary, because that's the only place where mixing is substantially different from zero. this is the part that I always find a bit difficult to explain, but I'll give it my best and you can ask all the questions you want. It's interesting in this problem, then you can predict the rate of overturning, the net overturning, from just the boundary layer solution. I think that's quite important conceptually, because it tells you it's the rate of upwelling along the boundary that seems to set the net overturning of the false solution. And the reason why you can do that, if you remember, is that you really have flow entering into the north along a deep western boundary current. Then it upwells along the boundary, way up, and most of it returns south, returns downward before feeding the return western boundary current. So you know, in terms of magnitude, the flow going up is more or less along the western boundary, along this boundary layer flows. The flow going up is equal to the flow going down, and they're also equal to the flow feeding in and feeding out. And your overturning is really the difference between the water coming in along the western boundary current and returning back along the shallower boundary current. And the transport is equal to that boundary layer, and that is what we are showing here, where here we show the overturning again in non-dimensional units, but this is how the overturning changes for different bottom diffusivities. And now we can use boundary layer solution. Here we're just computing the transport in the boundary layer along the upwelling branch, integrating over a whole sector in the northern hemisphere. And we're doing it at different isopycnal level, just to show you how much it depends on where you actually measure it. And you see that it really scales with the transport in the boundary layer. So what it tells you is that all overturning that you generally want to estimate with the kappa appropriate for the global basin is really only feeling the diffusive transport generated along these upwelling boundaries. That's the only place where the water is coming up, and you have analytical solution you can get that tells you at what rate the water is moving up, and that's the rate of the overturning. So if I change the slope, for example, I'm going to get a different overturning rate in this problem, which is definitely not something that enters in any of those scaling laws. So the abyssal circulation depends on the shape of topography. Yeah.
Are you talking about the mass transport or the buoyancy flux when you say up-down slope transport?
It's the mass transport. I mean,
mass transport.
Yeah.
Okay.
It is the overturning here. In this model, we don't have any eddies. So in any case, it's the Eulerian average mean on top of everything. That's the only thing there really is. We don't have a GM parameterization, even mostly because GM kind of parameterization mostly matter in the Southern Ocean when we are prescribing the solution to a prescribed stratification anyhow. So it's not particularly important, but that's definitely something one could move beyond.
Could you look, like you said, that the vertical boundary is like a singularity? Did you try to go to approach this singularity to see if it's actually a singularity?
So we know that if you go at the vertical wall, we can't even use these equations anymore because we can't satisfy the boundary condition. If you had a vertical wall, just horizontal friction is not sufficient. Either you put some vertical friction or some hyperviscosity and buoyancy, because now thermal wind otherwise gives a flow into the boundary. As soon as you have a tilted boundary, you only have bottom boundary condition. You don't have a lateral boundary condition. So you always have a W that allows to satisfy the non-normal flow boundary condition. So we know. Oh yeah, it's 10 to the minus 2 to 10 to the minus 3 in the real ocean. I think that there is a quote that I don't know from whom that says that there is always a bottom in the ocean, there is never a sidewall. Typically, yes, you find a bottom, the slopes are pretty mild, you don't get lateral walls. But what we know is that for those equations, a vertical wall is singular limit, because not only I would have to add, for example, a vertical friction, if I wanted to have a full self-consistent model. But if I add the vertical friction, essentially, then I have non-hydrostatic boundary layers, which are quite different. They don't satisfy this kind of dynamics. So at the very least, I know the vertical wall is a singular limit. If you go to small slope versus large slope, I don't know if there is. I didn't particularly explore. We changed slope, but we never went too steep because we have numerical issues if we do that. The whole problem, one of the things that's actually interesting, maybe as a side remark, just to get everybody seriously worried about any numerical model of the ocean. In order to solve this equation, we had to go into a sigma coordinate model. A sigma coordinate model is a model where you stretch your coordinates so that you have always the same number of grid points between the bottom and the top. We had to do that because we had to really resolve the flow along the boundaries very accurately. We need to have that resolution. If you don't, you always end up having steps in ocean models, and the buoyancy budget along those steps is not accurate, and you don't get these solutions. You need to go to a ridiculously high resolution before you get something close to this. And by ridiculous high resolution for realistic ocean topography, I mean you need a resolution of order 10 meters in what we find. Otherwise, you end up having spurious conversion rates. So it's not trivial, and I don't know exactly what it means for ocean circulation model and their overturning, but it's something to think about.
So you began with your lecture by explaining Stommel searching a trace of the upwelling somewhere in the ocean, something to be measured. So here, can we imagine to measure something related to this phenomena?
Yeah, so now the advantage is that, as I said, the vertical velocity along the boundary are still pretty weak, but they're not so weak that you can have no way of observing it. You're not talking about meters per year now, you're talking about fraction of a meter per day. So now that's an idea. We have a proposal that's what I spent my time doing the month before coming here. The idea is to go to a place that is called the Rockall Trough. Does anybody know where the Rockall Trough is? Yeah. I was looking at Alan. I mean, at least the Irish, it's just off Ireland. And you see it looks like a bathtub, so it's exactly what I want, because then I don't even need to change the configuration of the model. But mainly you have these sloping walls, and the idea is that indeed one of the main prediction of all this story is that while it's true that upwelling is not localized in one place, it is localized along sloping topography where it's rough and there is strong mixing. So if you go there, you should be able to see it. And the idea is to go along the eastern side of the Rockall Trough, where there is substantial tidal forcing. There is also a lot of hydrographic data, because biologists seem to like it because it's very productive. And the idea is that you can inject a dye, much like what Jim Ledwell has done for the ocean interior, but now we could inject a dye just along the boundary. Instead of using the very expensive dye that Jim Ledwell uses to measure them over years, you can put a fluorescent dye, and then with just vertical profilers, you can measure it continuously, and that dye should start moving by orders of meter in order of a week or so, which is generally the time for which you can detect a fluorescent dye before it decays. And so the idea is that, yes, we should be able to see plumes of upwelling flow. At the same time, in such an experiment, you could measure vertical profile of turbulence continuously, so you should be able to see what these profiles are. And for the first time, we're going to try to really measure W prime, B prime, because while going deep in the ocean is a pain, the advantage is that you have a solid boundary, so you can anchor your instrument to a place, so keeping instrument co-located is not as difficult as when you are vertical profiling. So we've done a set of test experiments. We can actually finally measure correlation close to the bottom boundary. And this boundary, the reason why we like the Rockall Trough is that it is deep, but it's only 2,000 meters deep, which is better than the average depth of the ocean, which is 4,000 meters. So you can do much more vertical profiling. So the expectation is that we should see fluxes like this. You should be able to see the buoyancy flux by measuring W prime, B prime coming back to zero. That will give us some information about mixing efficiency, because you remember W prime, B prime goes to zero, but epsilon doesn't, because there is plenty of kinetic energy in the boundary layer down there because of frictional effects. So we'll be able to measure what those values in the boundary layers are and supposedly confirm or reject the hypothesis if we don't see any upwelling in that part of the ocean. And I can conclude just leaving the name of the people that have been involved. They look all like convicts here, but they're actually nice people.
Why is Greg photo larger than the others?
Because he's the only one who didn't provide a picture, so I had to look for it. So that's all I could find. This is Jorn Kallis, was a student in my group that now is a faculty at Caltech. Ali Mashayek has run most of the the simulation we've seen in the first part of the talk. He's now, I guess, about to start a new job at Oxford or Imperial College. Henry Drake had just started at MIT, and Greg, you all know Greg. And he's at MIT when he's not traveling around. Thank you.
So, considering that in your model a lot of stuff happens near the boundary, one would think that if you were to go and look at observations of tracers in the ocean, like oxygen or silica or something, you should see these sources of tracers at a boundary in an isopycnal and emanating properties out from there. Do you see that anywhere, maybe in the Pacific or?
So that's a very good question. So why, the obvious thing would be, why then do you see plumes of temperature or oxygen, of radon moving along the boundary, and you see that upwelling? And the answer is no, you shouldn't expect to, because the problem is that while there is a pretty strong, what we call cross-isopycnal flow along this boundary, it's still orders of meters per day, and you're competing along a long isopycnal stirring, which is going to have velocity which are orders of magnitude larger than that. So what a real parcel actually do, or I think one way to think about it, so if you're looking at the tracer instead of what buoyancy does, and this is your boundary layer, the parcel is, and these are my density surfaces, so your particle will move up slowly, but then it gets affected in the interior, then probably gets reentrained in the boundary, it goes up, and so it goes into a spiraling world where it always occurs in the interior. Maybe I should do it even better. In the interior there is sinking, right? So a trajectory of a particle is really going up, then sinking a bit, but not as much as it did drift up in the boundary layer. So here it's the upwelling and downwelling, upwelling and downwelling. So what I'm saying is that the tracer is very good at averaging between the upwelling and the sinking in the interior, so you just get some smeared view, which is the net upwelling plus downwelling. So any tracer that you inject for very long times is not good at separating the upwelling of water mass along the boundaries versus the sinking in the interior. It gives you an average of the two. So you well, mm-hmm. I'm not so sure. You have all these zonal flows that are transferring the boundary information in the interior, right? That was part of the solution. So now it's a matter of time scale. Is there enough of a difference? Maybe there is, maybe there isn't. I don't know. Yeah, that's probably a good point. You say just to look essentially whether waters in the interior are much older, and you pick the tracer that can tell you. Yeah, that would be a good way to do it.
Do you talk with ocean ecologists at all to see if there are biological markers which might reflect, say, the upwelling in the edges of the Rockall Basin and that place?
Well, I don't know about the Rockall Basin, but one thing that we are looking into is, now it's getting into esoteric for this audience, I think, but it's delta C14, a tracer that is decaying over time. And what is definitely the case there is, and delta C14 is a tracer that can be measured very accurately, except that we affected it a lot with thermonuclear explosions that have a strong imprint. So you have to go before the thermonuclear explosion, and that reduces a bit the coverage you have. But the little you have tends to show that if you look quite deep, so below 1,000 meters or so, if you look above 1,000 meters, you see mostly the effect of the wind-driven circulation. But if you go below, indeed, especially in the Pacific, you tend to see that there are signatures of very old waters along the perimeter of the ocean, much older than in the interior, like there is this upwelling of dense water along the boundary. So at least it's consistent with the picture. I wouldn't say it's a proof of anything. It's also sparse data, so you have to be a bit careful. But that's one thing we looked at. In terms of biological markers, I don't know, because there isn't much life that deep down there that is easy to measure. There might be, but I think tracers, if there are clever ways, probably would be the way to go so far. We are working on this. It's not we have completed the story.
So most of the ocean model have very decent topography in their setup, and but they don't have the buoyancy flux as one of your main key driver of the enhanced mixing along the slope. So I was wondering, one of the take home from this very idealized work is maybe we should add enforce a buoyancy flux in those ocean model. Is that the right way to go?
I think it's a bad idea because you want the feedback between stratification and kappa, but you want probably, there are models that are already running that configuration where you have realistic topography and a profile of kappa, which is a function of height above topography. Then you have the element. The problem that you still have is that the resolution of those models towards the abyss is incredibly coarse. So for example, you get 300-meter resolution. So what you mean by your boundary layer thickness, how you resolve that upwelling and downwelling is questionable. And on top of it, I told you that you have all these problems that the models really have these discrete steps. So they don't really get upslope and downslope flows because this warm flow is trying to move really up along the boundary. But if you shoot it up in the interior, all of a sudden you mix it with the wrong water mass, the one is sitting above it, and it just stops. So you need the resolution in order to do it properly. We try, I know that we try with the MIT GCM, seeing whether if you just prescribe a profile of kappa T as a function of height above the bottom, what you get. Yes, you get water mass transformation not inconsistent with what I'm talking about, but they seem to be all happening in funny places where it shouldn't be happening, much closer to in the interior than the boundary. And it had to do with issues of resolution. We had to push a much higher resolution to start seeing something that looked like the analytical solutions.
Do you have any idea which kind of slopes are the most efficient to bring water up, or is it somewhat independent of the slope?
Well, and the reason I'm posing every time I have to remind myself, I know that the velocities are larger on flatter slopes, but since they are flatter, they transport less property upward because they project less in the upward direction. I don't know, we could look. I think that the evidence was more that what really matters is whether you're over rough topography where you have strong mixing. That those are the places that tend to dominate. The variation in slope were a second order effect. They weren't large enough. I mean, you're not going to find flat slope with a lot of rough topography because generally you have a lot of roughness on new crust, and that is mid-Atlantic ridges water is mass that is pushed upward and creates a slope.
I just wanted to ask again here, if I understand correctly. So in those planetary geostrophic equations that you wrote down, you included a Rayleigh friction, and not a, say, diffusive type friction.
Yeah.
Could you say again why that was sufficient to consider Rayleigh friction?
So if I don't put friction, I cannot satisfy boundary conditions. So that's why you need to do something.
Yes.
You could use a diffusive closure. It's just harder numerically because now resolving those boundary layer becomes more difficult. So it was just that it's the simplest problem where I could at least satisfy the boundary condition. There wasn't any more defense than that. That said, Henry Stommel used it to solve the gyre circulation, a similar problem with Rayleigh friction, and got quite a bit out of it. So we decided it wasn't an unreasonable thing to do. To be fair, these equations and the discussion on the importance of Rayleigh friction is something Rick Salmon have worked quite a bit on. And here I think the only thing we added at the beginning, what we didn't know was whether you would still get this upslope, downslope pattern of circulation, because those solutions starting from Phillips have always been obtained using maybe a more sensible diffusive law, so just the Laplacian of the velocity field, right, the classical frictional term. But it turns out that you get them also with a simple Rayleigh friction. So qualitatively, we felt it was easier numerically, and qualitatively was getting us the same solution. So we started the easy way. There are also some, well, we can discuss, maybe later I can just mention it. You always think that Laplacian diffusion is a more sensible representation of the solution, but it turns out under appropriate conditions here, you find a situation where you don't converge to any solution. The system never converge to a stable stratification. So you don't reach a steady state. There are some funny aspects of those solutions, and which you don't with a Rayleigh friction. So I'm not even sure whether the problem is completely well posed. Maybe the mathematicians in the room can help us and see whether there is something funny about the way the system is set up. But with Rayleigh friction, you don't have those problems. And there is always the answer that I write from Rick Salmon, says that if the details of the friction really matter, probably you shouldn't believe anything in your solution anyhow, because none of those closures is probably sensible to the extent that the basic pattern don't depend on the friction you use, which is the case at least for the boundary layer part. That's how we defend it, or why we decide to go that way.
Would you expect that geostrophic eddies could play a role in this picture close to the boundaries, because they could be local? volcanic instability and so on?
Absolutely, yes. So first, let me start upstream a bit. We used planetary geostrophy. Another good feature from our point of view to start simple is that, as far as I can tell, there is no absolute principle that tells us that no time dependence should develop planetary geostrophy, but the experience that it doesn't. So we get very easily steady solution, and we don't have to worry about time-dependent components. So we don't have any geostrophic eddies because the system cannot generate them, or the dynamics we use. That said, it's quite likely that if you allow for geostrophic eddy variabilities to develop, I don't think it changes anything in the qualitative picture of what is the boundary layer structure, because those are mostly along isopycnal flows. But it can affect definitely a lot the transport tracer in and out of the boundary layer. So for the tracer part of the picture, that would definitely be an ingredient you have to look at, because when I draw this kind of trajectories, they don't happen in the model that is set up, because these zonal flows are much weaker than they should be with full variability. So that would be worth exploring, but we haven't yet. In terms of the large-scale dynamics, as Paula showed us yesterday, the geostrophic eddies mostly matter in the Southern Ocean, where in any case we've been even less, or at least our shortcut was even so dramatic that we prescribed the stratification there. So the geostrophic eddies are already represented in the mean stratification we impose. So there is where you would have to do something if you want to move a bit beyond what we've done.
Do you think a even more idealized simulation, when it's just focusing on the boundary and there is no prescribed turbulence parameterization, will help to understand this boundary layer better? So it's a DNA simulation.
Exactly. Yeah. This is what Greg should be doing. So yes, I really think so. Yeah. It's a combination of measuring it and simulating to understand a bit the fundamental dynamics, which I think we don't yet as much, because most of the literature on boundary layer flows likes to stay on flat boundary layers unstratified, and here it's quite different. And there is literature and people that work on this problem, but I don't think there is a fundamental understanding yet, especially in the deep ocean, which is quite different. There is no external forcing acting there.
So I have two questions about the future. So first, during the last few years, each time I am following a lecture about ocean dynamics, I see that something very new came up about the overturning circulation. So do you think we are in a process of converging towards a general understanding of the ocean, or what is your feeling about that?
I think so. I mean, maybe I don't know. I enter in the field maybe too recently, but I would contend until 25 years ago, we liked to talk about the overturning circulation, but there were no real theories or scaling laws that people could really predict. It was mostly graphics. People talking about the thermohaline circulation. Now we heard Bill telling us that such a thing doesn't even exist. You cannot only drive thermally a circulation. So people went back, and I think one of the biggest contributions is definitely the recognition of the controlling role of the Southern Ocean. That's pretty recent, and allowed a lot of the scaling laws that Paula has described as something we didn't have. I find that it's always hard to know what you don't know, but I remember Bill writing an apropos for NSF at least 20 years ago, 25 years ago, saying that the basic of the ocean circulation is on solid footing, and now there are a few more issues that we have to resolve, but he couldn't see fundamental change in the understanding. And then you go back and you think that if somebody asks you the question of why is the 2-degree temperature in the ocean at 3 kilometers and not somewhere else, 3 kilometers depth, we didn't have an answer because it wasn't clear. I mean, you can try, it was based still on diffusive argument, but there wasn't anything fundamental. Now, how you project how the Southern Ocean plays a fundamental role in setting that stratification allows you to answer a question as basic as that. So I think that that was fundamental progress, and now it's pretty clear that that's the way the system works. It might be that we get better scaling laws, but at least the fundamentals are understood. I think in the Abyss, we start now mostly because the observations are coming online now. We didn't have as much even, I mean, the last experiment that put a lot of these elements together has been run in the 2000s up to 2015, so it's pretty recent. So my guess is the measurement in the Southern Ocean really changed the way we think about the problem. We started running models with the Southern Ocean. A lot of the fundamental works on abyssal circulation generally in the 60s and 70s was running without the Southern Ocean in closed boxes. Now you understand that that has changed. So my answer is that yes, I think we make important progress, and that will stay. And now we do have theories that are based on real GFD and how that situation works. It's not just simple models that come out a bit of nowhere. You know, when you think about Stomer's argument, they are really great in terms of insight, but it's not clear that there is a full building up based on fundamental equations that start from they give you the full solution. They just take some parts of the solution as given, like the upwelling, and then they see what happens. Now there is a full dynamical system that is connected.
So as far as I understand, and as we have seen today, so you rely a lot on the observed stratification. I guess you clearly explained that you were using this as a milestone
in the Southern Ocean.
In the Southern Ocean, and so I wonder now if you would not know the stratifications. For instance, if we are thinking of a different climate, so would you be so confident to be able to predict actually the overturning circulation, or actually the stratification itself, or different climate?
At this point, I'm not so sure I'm very confident that even at present day, the numerical model we use can produce a sensible stratification. Typically, stratification and overturning. Typically, the way they do it is you pick a kappa, a turbulent diffusivity that seems to give you the right pattern in a zonally average sense. If you believe anything of what I said, probably the real pattern of diapicnal flows are not going to be quite consistent, because you don't generally use profiles of kappa that have the right vertical structure and the right inhomogeneity as they should. So in a zonally average sense, they might still be alright, but in the details, they might still be pretty far off. But I agree that if you want to solve the full problem, this is the part we haven't done, but we can start solving this model and add the dynamics of the Southern Ocean. There is nothing preventing it, and then you can actually solve for it. We just haven't done it yet. And then you'll find out that there is a competition between the Southern Ocean affecting the overall stratification, and then the two have to come to equilibrium. Paola kept putting matching conditions, so you need to know both parts of the solution, you match them. This is just a starting point, given that we claim that we know what is today the Southern Ocean stratification. We can at least ask, if I know that, how does that information gets communicated to the rest of the diffusive abyssal ocean? But it's not the solution of what is the final state, because I had to use some present day information in the past climate. I don't know what that is, but I can solve that planetary geostrophic problem with the Southern Ocean, so I could do it.
Yeah. You could just add a channel into your geometry.
Absolutely.
And instead of Rayleigh friction, put a parameterization in the momentum equation as suggested TWA with vertical friction of U instead of Rayleigh friction, wind stress at the surface, and Bob's your uncle.
Absolutely, except for the fact that we had to write the sigma coordinate model, and it was an absolute nightmare. And that's what dictated really the choice of Rayleigh friction, because putting derivative was becoming very inaccurate. We didn't know how to do it. So it's, in theory, it's easy. In practice, I'm sure there are numerical people that are much better than us and can probably do it. So that's why here we stopped at that point. But yes, definitely you can. And it ought to be done at some point. That's the final part of the story. I think that the adiabatic circulation Paola has described is on much solid footing at this point, because we understood it enough. It's now coming to the point of understanding also what the abyssal structure might be. And here topography plays a big role, and that hasn't been fleshed out as much, but we'll get there too. And then we'll have probably an understanding of the abyssal circulation which is on par with the one of the wind-driven circulation that has been with us for a much longer time, and nobody's disputing that. So it's just that we are moving down. The waters here move much slower, so I think that part of the problem is, again, we are in a field that is dominated by observation still, and the abyssal ocean wasn't as well observed until recently, so it was hard to make theory that you could compare to anything. While the wind-driven part you could, so much more progress was done early on there. The atmosphere in some sense has that advantage, at least you can see through it. So some basic understanding is already there.
Okay, so I think you should thank again Raffaele for a very interesting lecture.